Good morning, everybody. Welcome to my talk, and thank you for the introduction. So yes, in this talk we're going to explore a little bit into distributed systems and Erlang and Phoenix and all the building blocks of the framework, and how, in a way, we plan to change them, but also pull out some abstractions that will be useful for other that we hope will be useful for other use cases. So I think the first thing we should a bit explore what distributed systems are. In general, this is any systems where you have more than one computer and they communicate with one another, right? So this creates a lot of problems that you wouldn't normally think about when just working on one computer. On the other hand, in the Erlang ecosystem, we already program in a style that is quite compatible with it, with processes and everything. So yes, this is me on the internet, the 12-year-old. And you can find me on GitHub and everything, usually under my name, because I'm not very good with inventing names. And right now, I was awarded the Mozilla Open Source Award, which is a program that Mozilla created to help support open source projects. And that's why I'm able to work on the Firenest project. Yes, this is a way for Mozilla, which is based on open source values, to give back into the community. And the reason they decided to support this project is because they actually use Phoenix inside Mozilla. It is used by the team called Mozilla Mixed Reality, which is quite interesting, and you can learn more about them. But in particular, they have this one project, one product called Hubs, which is this idea of a multiplayer virtual reality space where you can talk to other people and do meetings and things like that. This is how it looks. So normally you do this through VR headsets, right, or some other things. And in general, you can have multiple people, and you have this world. And actually, the Mozilla team, they have their weekly meetings inside VR, right? And I participated in a couple of them. So you can see, like, there are some groups that are like placed around the space, right? Couple people here, couple people there, talking with one another, and they don't overlap, right? So this creates a unique situation, right? How you can a future of meetings, right? In a way, maybe that's a solution for the meeting that have like 20 people and just 2 speaking, and the other people are just wondering what the hell they are doing there, which is usually the case, right? So yeah, why Firenest, right? There's a lot of things already, right? We have OTP itself, which tackles the distributed systems, right? We have PG2, we have Mnesia, we have the global module, and then we also have many libraries in Erlang, like GenLeader, locks, that generally focus on building those systems that span multiple nodes in different scenarios. But there is one problem with a lot of them, especially the ones that are built into OTP, is that they were built with a different network topology in mind from what we have today, right? Today, most applications run in the clouds, right, where the network is very unreliable. Like, network partitions are frequent, and most of the tools inside OTP, they assume the network is reliable. They were mostly built with computers inside a single data center talking to one another, when the network is very reliable. And obviously, this is a distributed systems talk, so we cannot omit the CAP theorem, right? Which is the most famous one, but probably also the most misunderstood one. I'm not going to try to explain it in depth, but the short description is that it's a classical pick-2 problem, right? So you have consistency in a way that every read is received by every read that you do in the system receives the most recent write or an error, right? This is the consistency. The availability, which means that every request is either satisfied or there's an error, right? And partition tolerance, that the system can operate in the phase where some messages are either dropped or delayed or reordered, right? And in general, this theorem says you can just pick 2 of the things, right? You can either be, and in general, you cannot leave out partition tolerance out, right? Because networks are unreliable. So you can generally find the CP or AP systems, right? And so this is exactly the problem that I talked about with the standard OTP tools, that they assume the network is reliable, right? So they try to be like AC, right? Consistent and available. But the problem is that when the network is partitioned, this creates a lot of issues. For example, with reconciling amnesia, like if any of you had to do that, it's not very nice. But we also have in the ecosystem other tools that deal with this issue, right? We have RIA Core, we have LASP recently. There are great tools that tried exactly to solve this issue, right? That to build the systems for an unreliable networks and to construct all those solutions. But the problem is that this is the situation, right? So you either build a single node application without anything, right? Or you build this huge application with like a lot of things with RIA Core or with LASP, but there's not this middle ground, right? We don't have the tools where you have an application that doesn't fit 1 node and you need 2 nodes, right? Building RIA Core when you need 2 nodes is like pretty absurd, right? And so this is, and the problem is that most people that venture into Elixir, or like Elixir in this case, right? They build their Phoenix application and everything is nice, right? It runs on single node, handles a lot of traffic, but then they need a second node, either for reliability reasons, right? Or for scalability, whatever it is. And then they arrived at this point when they have no idea what they're doing, right? And it's like, yeah, here we go. There's like React and have this, right? Build it yourself, right? But most of the problems that all those people encounter are pretty standard among the applications, right? And so this is the idea behind Firenest, to provide those common abstractions, common solutions to those frequent problems, or at least be a platform that we can build those common solutions on, right? We already managed to build such platforms for databases with Ecto, or for web with Plug and Phoenix. So why cannot we do this for this other domain? And yes, you're going to arrive at a point where you need those super customized solutions for those huge applications, but we already have solutions for this, right? So this is not really a goal for the Firenest project to cater to those very, very specific applications. And Firenest wasn't born in a void, right? It is connected to other projects, especially to Phoenix, because Phoenix already has huge parts of it. So as part of Phoenix, there's this Phoenix PubSub project, which has 2 main components. The PubSub itself, which is not surprising. So this allows many nodes that are in a cluster to communicate when you do Phoenix channels with one another. And the other part is Phoenix Presence and Tracker, which is like an implementation of it. And the idea of that was that now you build a chat application, right? And then you want to show who is online currently. And it turns out it's a surprisingly hard problem, right? So Phoenix Presence is this ready-made solution for this concrete problem that a lot of applications, a lot of people that build applications with Phoenix and with channels face and need. So it is a very interesting solutions in that space. I mean, the regular solution for that, like the easiest one, is like you have a central database and every node writes to this database, who's online, right? And then you need to read from a database and all is nice. The problem is, what if the database fails? And I believe even harder problem is, what if one of the nodes fails, everybody's disconnected, but now the node that was responsible for erasing the information that the people are gone now is dead, so you have inconsistent data in this central database, right? So Phoenix Presence implements this leaderless solution, right? Where all the nodes are talking one to another without any central point of failure. It is based on CRDTs and implemented on top of ads. The implementation is pretty complex, and it's also one of the solutions to venture into Firenest and try to rethink this, how we could simplify it. Yeah. If you want to learn more about Presence and how it works right now, there's this great talk from Chris at ElixirConf EU 2 years ago, I believe in Berlin also it was? Yeah. It's called Phoenix 1, 2, and Beyond. So yeah, I talked about why, I talked about like different things, but what is concretely Firenest right now? So it's a couple of components. It's still in work, right? So we're still exploring what could it be and how it could work. But in general, as I already said, the idea is to have this set of building blocks for distributed applications, right? To have this set of tools that you can use, and then maybe some libraries that provide solutions for concrete problems. So yeah, right now this is those 4 elements. So topology, PubSub, synced server, and replicated state. And I'm going to talk a little bit more about each of them and explain what they do. So topology is this abstraction around network, right? It is responsible for deciding how nodes are connected and disconnected, how failures are handled, how you send messages, how you broadcast inside a cluster. It's basically a behavior, right? And you can have multiple implementations. The standard implementation obviously will be the distributed Erlang, something we already have that does it. But before we release, we also want to have one based on Redis to achieve parity with Phoenix PubSub if we want to replace it. But something more further along the line is leveraging the Partisan library from the LASP project. That the goal is to provide a scalable distribution layer for Erlang, because the standard one has scalability issues, both hundreds, like depending on the application, right? 50, 100, 150 nodes, but like that's the general scale you can expect. If we can leverage somebody that already is doing a great work, why not? So this is some idea. And one thing we want to also explore is having a test topology that will generally allow you to have multiple nodes inside multiple logical nodes inside a single node, real Erlang node. And the goal for that is to have very fast tests, right? You can use the slave module or like spawn additional VMs, but doing that for each test is very, very slow, right? It takes a lot of time. It's a great way to test your system when you can spawn a new cluster for each node and then shut it down, but it's very slow. So this is an idea and vaporware at this point, so don't hold me to that. But the idea is to have this nice thing where we could test this and spawn new cluster just as a set of processes inside the VM. So yeah, the topology, it provides couple things, right? So you start it as in your supervision tree, and then you have this 4 main functions, right? Which is like connect and disconnect, where you can connect and disconnect nodes from your cluster, and then you can broadcast to a named process on all the nodes, right? Or you can send to a particular named process on a particular node, right? So this is the general API. It deals with named process, right? So it doesn't the topology itself, it erases this idea of PIDs, right, from the distribution. So we only have names. And another building block, which everything else builds on top of, is this idea of synced named. So what this does, it connects the process on your node, right, to all the processes with the same name on all the other nodes in the cluster, right? And you'll receive messages when a process comes up on another node, or a process goes down on another node, right? So this is the basic fault tolerance mechanism that we want to build this on top. We're not yet sure if this will be enough, but so far what we've implemented using basically just that abstraction is enough from the network to build all the features we wanted. And yeah, so that's topology. The PubSub is a very simple thing. It's basically also started in your supervision tree. You can subscribe to a topic, and then you can publish messages on particular topics, and that's it, basically. But what's I think interesting in a way is that it's implemented both on top of Firenest topology for the communication between nodes, but within the node for publication, it uses Elixir registry. So the whole implementation, I think, is like something like 100 lines of code, right? Which to me tells me it's like we're having good abstractions when you can implement things like that with such a few amount of code. I don't think we need to talk anything more about that. So the synced server is something we built on our way to the replicated state, which was our goal from the get-go. So the synced server is like a gen server, but with 2 additional callbacks, right? So the callbacks are handled remote, when you handle remote requests from another process, from another node, and handle replica when you handle the same process comes up or goes down on another node, right? And this already also handles the communication problem, because even with the synced name abstraction, right, when a process comes up on another node, so we know about this process, but it doesn't necessarily know about us yet, right? So it also implements this double handshake mechanism to establish the communication for like synchronous or like at least bidirectional communication. And then we have the functions to send to a particular node or broadcast to all the processes, right? So what we deal here with is that we have a named process on many nodes, and they are all connected to form a single synced server, right? So there is, in the callbacks, we're implementing some mechanism how we're syncing the nodes, the processes among the nodes. Okay. And we use this abstraction to build the biggest part so far, which is the replicated state, which is this idea of a key value store for ephemeral data, right? And so one example of such ephemeral data is Phoenix presence, right? So what I mean by ephemeral data is that each data is associated to a process. When the process dies, the data is gone as well, right? So in case of presence, we have the connection process, right, for the WebSocket or whatever, right? So as long as this connection is open, the user is online. So we have some data that indicates the user is online. But as soon as the process dies, the data is removed. Some other use cases we are also guide also the design is for example, a rate limiter, right, that you could implement, or some form of cache distributed in the cluster. The state is replicated incrementally through deltas, but it's up to you in the callbacks to implement what those deltas are. I will talk a little bit more about that. And what is also important is that it provides callback where you can react to precise changes in the state. Right? So for example, in case of presence, we need to send information to the browsers that somebody came up or somebody went down, disconnected, or something, right? So we need this precise tracking of the state changes. And yeah, as I said, the main goal is re-implementing Phoenix presence with some different approach without the CRDTs, right, this time. Because one of the things that we realized when we were trying to optimize the CRDT in Phoenix presence was that the CRDT solves the problem of conflicts, right? Basically, right, when you have multiple nodes trying to write to the same data. But here, because we're dealing with ephemeral data, we really don't have any conflicts, right? Because each data is associated to one process, only that process can change this data, right? So there's no inherent conflict in the data, which means, in principle, we don't need a full-blown CRDT, right? So we can try to simplify the implementation, maybe also make it more efficient along the way. So the main API of replicated state is just those 4 functions, which is put, update, delete, and list, right? So as you can see, for all put, delete, and update, you both provide a key and a PID, right? So the state is associated to a key and to a PID, right? And then when you list it, you list the data from all the PIDs in the whole cluster, right, that are associated with this particular key. And I'm not sure that's very readable, probably not, especially in the back. But we have a couple callbacks to deal with it, right? And there are two groups of them. So first, there's like the traditional init callback, right, where you establish some initial state. And then there are local callbacks, right? So whenever you call put, there's a local put that will be called on the server. Whenever you call delete, there's local delete. Whenever you call update, there's local update, right? And those callbacks are responsible for maintaining the current state, so the value for the node, and the data, the delta that will be replicated to the remote servers, right, by the process, by the mechanism. And the delta can be whatever you want it to be, right? For example, in case of a presence, this might be a list of updates like joins and leaves, right? In case of a counter, it might be just like a number, right? So we think it's quite flexible, and it will allow us to implement efficiently different operations. And then you have this callback that prepares remote delta, that takes the local delta that you are building and prepares it for broadcasting to other nodes. This step, in its most setups, it probably won't be necessary, but in case you maintain some additional state in the delta and want to strip it before sending, that's the place to do it. And then when you send this remote delta on a remote process, we have this handle remote delta, right, function that applies the changes from the remote node to the local state. And finally, there's this observe remote changes function that is exactly what I talked about, the precise tracking of the state, right? And the observed remote changes argument is like quite complex, so I didn't write it in here. But it allows you to know what exactly happened on every node in the cluster. And this is the part that we want to build as the next one, which is Firenest registry. So the main goal is to provide unique cluster registration. So something like global, right? But not based on logs and like global does it, but rather to base it on a distributed hash table, similar to what you have in Microsoft Orleans. So the Actor solution for .NET, or in Akka in Scala, right? They both have those kind of APIs, and we also think this will be a very useful building block for those distributed systems. And then there's the future, right? We have some ideas where we want to take it. So even more advanced abstractions, right? So maybe something like persistent actors that you can find in Akka, in Scala, right? Which is this idea that you have actors that are virtual actors from Orleans, right? Which is this idea that you have an actor that is always alive, right? And when you send a message, you just send it a message, and the system, if it routes it to the correct node, and then spawns it there. And if it's not alive, if it's alive, it just sends the message, right? And you, as a user, don't care about the life cycle of the process, where it should be spawned, and how it should be handled, right? You just send messages to it, and that's it. And the system manages it, right? So whenever it dies, it will be restarted with the state and all of that. And something more is reliable delivery mechanism, right? So at least once delivery for messages, which is also a useful building blocks for applications. So yes, I think that's what's mostly it from me about Firenest. I hope you learned something and I haven't confused you too much. It's still very much a research project, right? And trying to find those right things, balance them, and if it's something that is interesting for you, I would be glad if you talk to me and maybe would later work on it together, right? We're looking for contributors from other fields to explore that those abstractions we're building are actually useful, right? And not just seem useful to us, which is quite hard when building libraries. So yes, I'm not sure we have time for questions.
We have a lot of time for questions. So, yeah, any questions?
So you mentioned CAP. What is it? CP or AP?
Sorry?
You mentioned CAP.
Yeah.
So the distributed abstractions you're building, are they actually CP or AP? What are you striving for?
Or rather AP, right? So this is, so for example, with the sync server and the replicated state, you're generally not guaranteed to get the latest value, right? But in many things, like in the, for example, for presence, it's not a big issue. It's something similar to that journalists say, right? Wrong, but not for long, right? So because yeah, just like get the news out, and then you can correct it, right? If it's not right. So because the data changes quickly, it's not a big issue if it's slightly wrong for a short period of time.
Other questions?
Yeah, sorry. Is the abstraction meant only for data that is not persistent, or are you planning also to aim for some?
So right now, the goal is for the ephemeral data with the sync server, right?
Yeah.
With some other things, like, for example, the persistent actors, right? Those would be for the persistent data. There's also possibility of building some kind of thing based directly on CRDTs, right? And so some kind of abstraction based on CRDTs. So Akka has something They call it, I forgot how they call it. It's like distributed data, I think, or something like that, right? Which is this idea for like persistent data that is distributed in the cluster. But for now, we're focusing on this ephemeral use case because we think that that's the thing we want to replace. That's one side. And then we found it's useful in many areas where things for persistent data are used when they actually don't need to be, right? Yeah. So this is something we want to explore.
Thank you.
Yes?
Have you guys looked at cluster? And because you already implement some of the features you're working on, like
yes. So it was developed in many cases, like because the topology part of Firenest is pretty old, right? So it was developed quite some time ago. But yes, and we're looking at other projects, right? So to compare and contrast, but we want to build this from the ground up to also try to extract the parts, like basically lessons learned from Phoenix PubSub, right? Also in a way. So we want to go from that. And this is by no means, like it's still pretty far from being production ready, right? But we might end up replacing it with some library. But for now, we want to try to find also this minimal abstraction that we can do for a cluster. Yeah.
Thank you so much. Let's have another one. Thank you.